Okay, so in this video, I want to go through solving a system of equations by using row operations. Okay, so and there's lots of space because this is going to take some some space, and you want to write neatly, keep track of your work, as organized as you can. Okay, so the first thing I want to do is rewrite this problem into an augmented matrix. So I'm kind of paying attention to the columns, and I'm noticing that each of the rows is missing a variable. So it's really important that we keep a placeholder. So when I start here, I've got 1x, negative 1y, no z's, and then 6 is my constant. The second one, I have got 2 x's, I've got 0 y's, and negative 3 z's, constant is 16. And then the last one, I've got 0 x's, 2 y's, 1 z, and then 4 of my constants. Okay. Now, remember the goal of row reduced echelon form is to make sure that you've got a 1 in that upper left, entry, which we do, which is great. If it's not, then we'd have to do one of our 3 kinds of row operations to get that. Okay, so then what I'm going to do is I'm going to use that 1 to pivot. I'm going to knock out that 2. So I'm going to say negative 2 row 1. I'm going to add it to row 2, and I'm going to put it in row 2. Oops, sorry. So then my new matrix, row 1 is not going to be altered. It's still going to be a 1, a negative 1, a 0, a 6. And row 3 is still going to be the same, 0, 2, 1, 4. Sometimes I like to do that, like get rid of the ones that, or like do the ones that I don't have to change first. Okay, so then negative 2 times 1 is negative 2 plus 2 is 0. Negative 2 times negative 1 is 2 plus 0 is 2. Negative 2 plus times 0 is 0 plus negative 3 is still going to be negative 3. And then negative 2 times 6 is negative 12 plus 16, which is 4. Okay, so once we do that, then our next job is to get a 1 in the next entry. So I want to make this a 1. And so, I mean, I can do a couple different things, but I usually just multiply by its reciprocal, that row. So I would multiply row 2 by 1/2 just to make that a 1. I think it's easier than doing a linear combination. So my row operation language then would be 1/2 of row 2, and it's going to stay in row 2. So again, maybe we just then can very quickly write down row 1 doesn't change. 1, negative 1, 0, 6, and then 0, 2, 1, 4. But now when I do half of row 2, well, that's still 0, but now that's a 1. That's negative 3 over 2, and then that's a 2. And then once I know that that's a 1, right? So once I have that to be a 1 right here, then we're going to use that to knock out the above and the below. So a linear combination to make those zeros. Okay, so then my next row operation would be, let's say, row 2 plus row 1. Since they're already opposites, and let's put the result into row 1. And when you get really good at doing these, you could, if you want to do another step, we could, in the same matrix, say do negative 2 of these and add it to that. I'd be okay with that too. But since this is our first example, let's do them separately. So our next matrix then would be, I think I've got room here. So row 1 is the one that's changing. So 0 plus 1 is 1. 1 plus negative 1 is 0. Negative 3/2 plus 0 is negative 3/2. 2 plus 6 is 8. And then this row doesn't change. 0, 1, negative 3/2 and a 2. And this one is 0, 2, 1, 4. But then, just like I said, we're going to go ahead and now do negative 2 row 2 plus row 3. And let's put it into row 3. So go back to our black. So that means row 1 and 2 are not changed. So it's still 1, 0, negative 3 over 2, 8. And then this row is 0, 1, negative 3 over 2, 2. But now here this is 0. Negative 2 times 1 is negative 2 plus 2 is 0. Negative 2 times this would be positive 3. Plus 1 is 4. And then negative 2 times 2 is negative 4. Plus 4 is 0, which is nice. So then what we'll do is make the next one, that third one down the diagonal, a 1 as well. Make this guy a 1. And the easiest way to do that is multiply by 1/4. So my row language, my row operation, oops, go to a pen first, sorry, would be 1/4 of row 3, and let's leave it into row 3. So back here, so row 1 and 2 do not change. 1, 0, negative 3 halves, 8, 0, 1, negative 3 halves, 2, and this is 0, 0, 1, 0. Okay, so now, even though I kind of start, I know what some answers are, I could go back and back substitute. To get this in row reduced echelon form, remember that's something that we should remember from the last video. Row reduced echelon form not only has ones down the diagonal, which what we have, right? Ones down here, but it also needs to have zeros in this, all the upper entries. So I still need to use this 1 here, and I'm going to pivot that 1 and knock out those values. And it's going to be really easy because, well, there's a 0 there, so that helps. So let's look again, just to take this through to fruition so we can see exactly that row reduced echelon form. I'm going to do 3 halves row 3, add it to row 2, and leave it in row 2. And I might as well just do 3 halves row 3, add it to row 1, and put it into row 1. Since both 1 and 2 are independent of each other in this particular row operation. So row 3 is the only one that's not changing. So we'll do that. And then, so if I do 3 halves of 0 plus 0, it's still 0. 3 halves of 0 plus 1 is still 1. That's why we do them in this order. 3 halves of 1 is 3 halves plus negative 3 halves is 0. And then that becomes 0 plus 2, which is 2. And then the same thing here. 3 halves of 0 plus 1 would still be a 1. 3 halves of 0 plus 0 is a 0. 3 halves of 1 plus negative 3 halves is a 0. And then 3 halves of 0 plus 8 stays my 8. So that is row reduced echelon form. And again, we know that it is a row reduced echelon form because we have a 1 down the diagonals and the zeros are everywhere else other than our solution column. So then this tells us that our first one, x, is equal to 8, that our second one, y, is equal to 2, and our last one, z, is equal to 0. So it's the ordered triple, 8, 2, 0. And, if you check your work, go back up here, just double check. So if you do 2 times 2 plus 0, yep, we get 4. 2 times 8 is 16, minus 0 is 16. And then if we do 8 minus 2, we get 6. So definitely this is a consistent system, and there's exactly one solution, 8, 2, 0. Okay, now let's also look at example 2 together as well. So again, thinking about taking this and first writing it as an augmented matrix. So 1, negative 1, 1, 8. And then 2, 3, negative 1, negative 2, and then 3, negative 2, negative 9, and 9. And I'll be the first to admit that this is not the most efficient way to solve, right? But what we're looking at is just a method to solve. It's a way to practice using matrices. But then, and also, and probably more importantly, it's going to be a way that we can understand perhaps the programs that our calculators will use to help us solve this very efficiently, to say the least. So I get it. It's a little bit tedious. And so, I won't always have to do it this way, but it's part of learning about matrices and how they can be used in structure solving these systems. Now, since I already have a 1 here, which is great, I'm going to use that and knock out this 2 and the 3, and I'll do it in the same row operation. So I would say negative 2 row 1, add it to row 2, put the result into row 2, and let's do -3 row 1, add it to row 3, and then leave that into row 3. So it kind of combines those together. So row 1 is not changing, right? Only row 2 and row 3 are. So 1, -1, 1, and 8. And then this will be -2 plus 2, which is 0. -2 times 1 is 2, plus 3 is 5. -2 times 1 is -2, plus -1 is -3. This will be -16 plus -2, which is -18. And then this one will be -3 plus 3, which is 0. This is -1 times -3, which is 3, plus -2 is a 1. This is -3 plus -9, which is -12. And this is -24 plus 9 would be -24 plus 9 would be -15. Okay, so now I want to get a 1 in the middle. And I think I might just do a row swap since there's already a 1 here. So what I might do is just swap row 2 with row 3. So that way I do have that 1 there. So when you do a row swap, it's probably best to just do 1. So 1, -1, 1, 8. So now the new row 2 is 0, 1, -12, -15. And then this row is 0, 5, -3, -18. And I'm so carefully looking back and making sure I'm not making any arithmetic mistakes because it is so easy to do that, right? I mean, so hopefully I haven't made any yet. But now I'm going to use this 1 and knock out above and below. So I might do just row 2 plus row 1 and put the result into row 1 because that's going to make that a 0. And then I might do -5 row 2, add it to row 3, and put that result into row 3 because that would make that a 0. So let's get that next matrix then. So row 1, so 0 plus 1 will still be 1. 1 plus -1 is 0. -12 plus 1 is -11. -15 plus 8 is -7. Row 2 did not change, so it's 0, 1, -12, -15. And then when I do -5 times 0 plus 0 is still 0. -5 plus 5 is 0. This would be 60. Minus 3 is 57. And then, -5 plus, -5 plus, -5 times -15 is 75, minus 18 is 57. Oh, phew, that's a nice thing, right? Let's make that a 1 by multiplying by 1/57th of row 3. And that it doesn't guarantee that it's right, but that's a good sign that that's divisible. Okay, so 1/57th of row 3, and let's put it into row 3. So then row 1 stays the same, which is -7. Row 2 stays the same, but now row 3 is 0, 0, 1, 1. So we really already know what z is. Z is 1. And we could use that to back substitute it to here, and then use that to back substitute there. But if I truly want row reduced echelon form, then let's use this 1 and pivot up there one more time. So let's just go ahead and let's do 12 of row 3 and add it to row 2 to knock that out. Then put the result into row 2. And let's do, that's an 11. So let's do 11 of row 3 and add it to row 1 and put the result back into row 1. So then when we do that, so row 3 does not change. So again, sometimes I like to do that just to get that one out of the way. And then let's go to row 2. So 0 plus 0, it will still be 0. 12 zeros plus 1 is still 1. Now 12 ones plus -12 is 0. And then 12 plus -15 would be -3. And then we'll do 11 up here. So 11 zeros plus 1 is still 1. 11 zeros plus 0 is 0. 11 plus -11 is 0. and then 11 minus 7 would be 4. So there is row reduced echelon form, because I know I have the highlight down the middle of 1s, and my solutions would sit right there. So then I can say there's one answer, one solution. So this is a consistent system, and I know that x is equal to x is equal to 4, y is equal to -3, and z is equal to 1. And you could check your work and pick, this ordered triple, so 4, -3, and 1. Pick any of them and check it. So that top one. So if I do 4 minus a -3 is 7, plus 1 is 8. Checks. 2 times 4 is 8, minus 9 is -1, minus another 1 is -2. Check. 3 times 4 is 12, and then become plus 6, so that's 18, minus 9 is 9. Awesome. So again, solving these by row operations, isn't necessarily the most efficient. But what I do want to emphasize is that it is an algorithm. It's a process. It's something that you can program a calculator to do, and actually our calculator is already programmed to do, so that once we do this by hand, we'll see, oh, our calculators, this is how they're doing it, and now I get the answer here, which is pretty cool. Okay, so rewind if you have any questions, or ask me if you have any questions coming into office hours.